All right, let's summarize where we were, where we are. We have learned our iconic triangles, 30, 45, and 60. And we learned the sine and cosine and tangent of 30, 45, and 60-degree reference angles going all the way around the circle. We've learned how to take those values from the first quadrant and put them into the second, third, and fourth quadrants. We also started talking about the unit circle, how going around the unit circle, we had the x-coordinate telling us the cosine of the angle and the y-coordinate telling us the sine of the angle. And so we saw the cosine start off at 1. Oh, I'll do from your perspective. Start off at 1 and drop down to 0 at 90 degrees in the first quadrant. Then in the second quadrant, go from 0 down to -1. In the third quadrant, go from -1 back up to 0. And then in the fourth quadrant, go from 0 back up to -1. So we saw the cosine start off at 1, drop down to 0, down to -1, back up to 0, and back up to 1. And we saw a sine follow the y-coordinate around. We saw the sine start off at 0, go up to 1 in 90 degrees, go from 1 down to 0 in the second quadrant, go from 0 to -1 in the third quadrant, and from -1 back up to 0 in the fourth quadrant. And since that's the direction that my mind took when I talked about where we were, that tells me what we want to do next, because I had a choice. I guess we had a choice, but I get too many votes in that. We either can talk about radian measure, or we can start taking the unit circle and stretching it out. And I think that's what where we want to go next. That's what I was trying to emphasize before. Any questions before we get started? There's a couple of new quizzes. They're called Know Your Values. It's not like your personal values, it's just like your reference angles and things like that. There's going to be 4 of them. The first 2 are about reference angles. Here's an angle, put it in the 4 quadrants as a, take this reference angle and put it in the 4 quadrants. Then here's an angle, identify the reference angle. Nice and straightforward. One of them has 12 questions, but it should only take you 12 minutes, depending on how good your connection is. And I think I had previously announced that there was a solving right triangles quiz number 4 with a bunch of stuff that I never told you about, like flying planes and horizontal and vertical components of forces. But we don't need to, because it tells you what to do. Solving right triangles, find the triangle and solve it. We know sine, cosine, and tangent values for our iconic angles. We know sine, cosine, and tangent values for the iconic angles. That's the 30, 45, 60, and the quadrant angles. So we've taken our unit circle and broken it up into our 4 quadrants. We learned about the sine, cosine, and tangent of our quadrantal angles going all the way around, and our 30, 45, and 60-degree reference angles going all the way around. So starting off at 0, we got 0, 30, 45, 60, 90. On the other, in quadrant 2, 120, 135, 150, 180. That was quadrant 2. Quadrant 3 starts off at 180, goes to 210, to 225, to 240, down to 270 at the bottom. There's quadrant 3. And then quadrant 4 goes from 270 to 300 to 315, 330, back up to 360. So those are all quadrantal angles and 30, 45, and 60-degree reference angles. And we know those values. The 30, 45, and 60-degree reference angles have sine and cosine of 1/2, √2/2, and √3/2. Tangent of 30 is 1/√3, which you might know also as √3/3. Tangent of 45 is 1. Tangent of 60 is √3. So we know all of our values going all the way around. Here's what we want to do. We want to take those values and stretch them out into a graph that goes sideways. Instead of having an angle theta that goes around in a circle, we want theta to stretch out along a number line and see what kind of graph we get. So let's remind ourselves of what we're going to do. So let's take our unit circle where we have theta starting off at the positive x-axis and going counterclockwise in the positive direction. And what I want to do is I want to take theta, and instead of having theta go around the circle, I want to stretch theta out along a number line. Theoretically, I shouldn't be doing this until we've talked about radians, so I can have trig functions applied to real numbers rather than just angles. And so there's a whole host of ancestral trigonometry instructors that are like, oh, Leach, what are you doing? You can't do this before radians. And I'm like, oh, watch me. And then I make the screens rise from the floor. See, it's much more dramatic in my head. Oh, that would be kind of excellent. Especially if I had pyrotechnics to go along with it. For tomorrow, there will be a test. That would be awesome. What are we talking about? Oh, yeah. We're going to stretch theta along a number line, and we're going to see what kind of graph we get. So here at this 45-degree angle, we know that our values are going to be √2/2 and also another √2/2. That's where they match. And that is approximately 0.7071. At the 30 degrees, our values are going to be a √3/2 and 1/2. And then at 60 degrees, we're going to be at 1/2 and √3/2. So we can see the progression of values. 1 drops down to √3/2, which is about 0.8660, drops down to √2/2, which is about 0.7071, drops down to 1/2, which is exactly 0.5, and then it drops down to 0. And then we get the same values with different signs. Remember, at any point on the unit circle, if I have an angle theta, the coordinates at this point are going to be cosine theta, sine theta. Now what we're going to do is we're going to stretch theta out along the number line. can barely see where the dots are. Too often I imagine that Simpsons episode, behold, the ravages of age. Messed up. So instead of theta going around in a circle, I'm going to stretch theta along the number line. So notice I made marks every 3. So, oh, hey. Now I can see both. So I put marks at 30, 60, 90, and then 210, 240, 180. Oh, sorry. 120, 150, 180, then 210, and then 240. So I'm leaving off the 45 degrees. I'm going with 30 and then 60, and so on. So this first mark here is going to be at a 30. And the next mark will be at a 60. Those are blue. And what we're going to do is draw the graph of cosine theta. So theta is going to be down here on this axis. Cosine of theta will tell us the x coordinate of the point going around the circle is the cosine. And so we're going to graph the cosine and see what the cosine looks like if we stretch it out over this number line. So the first point we're going to mark is up here at 1, because the cosine of 0 is 1. A little bit. There we go. So theta and cosine theta. So when theta is 0, cosine is 1. And so I'm going to mark that point up there. When theta is 30 degrees, cosine of 30 is root 3 over 2, which is about 0.866660. And then when theta gets to 60 degrees, we're at 1/2, at least that's easy to find. And then when theta gets to 90 degrees, we'll be down to 0. There's our first quadrant. We're going to see cosine go from 1, drop down to 0. So the easiest one to get would be cosine of 60 is 1/2, and that's easiest to locate. So notice that for 60 degrees out of the 90, 2/3 of the way, we spend dropping 1/2. And then that last 1/3 of the way, it drops faster. It drops another 1/2 in just 30 degrees of change. So it takes 60 degrees to drop down from 1 to 1/2, and then only 30 degrees after that to go from 1/2 down to 0. So it should start off kind of flat and then get steeper as we fall. I can 100% not see where the dots are. So It's going to have to approximate. The cheat for that is to draw a bigger dot. Now, before I connect these up, I want to keep going. So after 90, 30 degrees later is 120. And 120 is a 60-degree reference angle. So after 90, this point's going to be at 120. And then after 120, 30 degrees after that is 150. So this point's going to be a 150. So 120 has a 60-degree reference angle. So the cosine of 120 is going to be a 1/2, but it's in the second quadrant, so it'll be negative 1/2. So at 120, we still have the 60-degree reference angle. We'll be at negative 1/2. At 180, at 150, that's a 30-degree reference angle. Cosine of 150 is then negative √3/2. And then when we get to 180, cosine of 180 is down to negative 1. There's cosine dropping from 0 to negative 1 in the second quadrant. So from 90 to 120, we're dropping 1/2. In 30 degrees horizontally, we drop 1/2 vertically. But then it takes 60 degrees to drop the other half down to negative 1. So it's starting to flatten out. So the red spots correspond to the 30-degree reference angles. The blue spots correspond to the 60-degree reference angles. Now we can keep this going. We've got our values going around. After 180 will be 210. 30 degrees later is 210. And that's a 30-degree reference angle. And the cosine is back to negative √3/2. It makes sense because 210 is in the third quadrant. Cosine is negative in the third quadrant. So it's all coming together. After 210, 30 degrees later is 240. And cosine will be negative 1/2. And then at 270, cosine is back to 0. There's cosine going from negative 1 up to 0 in the third quadrant. So here's 210. And then 240. So at 240, that's where we're going to be at 1/2, or negative 1/2. And then at 210, we're going to be at that negative √3/2. And then a similar thing happens in the fourth quadrant. We're going to go from 0 up to 360. This will put us back at the beginning because we've made one complete circle. So in between 270, the 60-degree reference angle is going to be 300, and the 30-degree reference angle will be 330. We're here in the fourth quadrant where cosine is positive, because cosine is positive where x is positive, so that's the right half of the Cartesian plane. So at 330, we're going to be at √3/2, and at 300, we'll be at 1/2. And so we can see the graph start off at 1, drop down to 0, down to -1, back up to 0, back up to 1. And so we just try to make a flowy line. It should be flat here, flat down at the bottom, and then flat at the ends. Notice how it drops down slowly in the first 60 degrees. Then it has to drop down quicker because it's got to go to the same distance in half the time. Same there, but then it kind of slows down to flatten out. Then it continues kind of going slow, up, coming out of the turn. Hits the straight part, kind of goes faster, up through 270, and then it has to slow down to make another turn. Now at this point, if we keep going from 360 to 390 and so on, we're just going around the same circle. Remember what we did was we're just making a graph of the x coordinate going around this circle counterclockwise. So once we go all the way around to 360, we're going to see the same graph from 360 to 720, and then the same graph from 720 to 720 plus 360. And then the same graph from 720 to another 720. 1080? 1080? If I watch the X Games more often, I would know these values. So this is what the graph always looks like. It just repeats at this point. Which is that over and over again. Use music notation. If you're wondering where the coda is, there is no coda. It does this forever. We just put this on a loop. If we look at the circle that happened before 0, from -360 up to 0, it still looks like the same graph. So the graph of cosine of theta is periodic with a period of 360 in degrees. Cosine of theta is a periodic function with a period of 360 degrees. Every 360 degrees is just a copy of the 360 degrees that went before it. Every day is just a repeat of the day before. Imagine the jobs in your future where every day is just going to be a repeat of the day before. Hopefully you get a job that's not a periodic function. Or at least if it is a periodic function, it has a longer period. I have a job with a period of 1 semester. Questions? Which is great because if you teach a class every semester, all the mistakes that you make in the first semester, you make them at the same time in the second semester because it's been long enough to forget that you got to remind yourself to fix the thing that you did wrong before. So it's long enough to forget that you needed to fix that. Any questions? Periodic is a way we could describe a function that has a period. This particular function is what we'll call a sinusoidal function. So sine and cosines are going to be sinusoidal functions. And these are great functions for describing things that kind of go back and forth and just repeat. Imagine high tide, low tide, high tide, low tide, high tide, low tide. Just repeating that forever. Imagine a pendulum swinging back and forth, all the way to the right, all the way to the left, all the way to the right, all the way to the left, all the way to the right, at the middle, all the way to the left, back in the middle, all the way to the right. And it just swings back and forth and back and forth. Any questions? How's everybody okay? Sine, the graph of sine of theta will have the same shape. Only instead of starting off at 1 and going down to 0, in the first quadrant, we know that sine starts off at 0 and goes up to 1. So if you want to look at the graph of sine theta, we will make a much sketchier version. Sine will start off at 0. I didn't give myself enough space. Sine will start off at 0, go up to 1 in the first quadrant, and then back down to 0 in the second quadrant, then down to -1 in the third quadrant. Oh, I've gone too far this time. So here's our graph of sine, starting off at 0 when theta is 0, and going up So here's going to be one cycle of sine of theta. Here it is. Too long. This also reveals the trick to making a nice sine graph. Focus on the halves because those are easy to mark. So I just established one. It's easy to locate a 1/2, and just put the 1/2s at your 30-degree reference angles. So here we're at 0, 0. Here we're at 30 and 1/2. Then up here at the top will be at 90 and 1. And then here we are at 150 and 1/2. So the way I do this, I start off at 0, 0. Then I go over 1 and up 2 to get to the 1/2. And then I went over 2 and up 2 to get to the 90. So that I go up the same amount in twice the change in theta. Focus on the 1/2. Oops, negative 1/2. On the cosine graph, notice all the red dots were at √3/2 because the cosine of 30 is √3/2, and I've been using 30. I've been using red for the 30 degree representation. Here, sine of 30 is 1/2, so all the red dots are 1/2. Then if you want to pick out the rest, once you get a nice flow line, you can just say, oh, that must be where the 0.8660 is. Because here we are at 60 and √3/2. And then on the other side, that's where we're going to be at 120 and √3/2. Sine starts off at 0, goes up. Cosine starts off at 1 and heads down. Questions? Is everybody okay? Let's take 5 and talk about, come back and talk about more details that we want to put in and changes that we want to take place. All right, take 5.